Today we're going to take a look at Chapter 16, Acids and Bases. And you don't need to look at this. Brightspace has PowerPoints, it has the review document, and it has work problems. It also has the key. I didn't print the key out, but since there's nobody here, that doesn't matter. Let's see, let's put that up there. Okay. Got another one zooming in. Okay, we're just getting started. All right. Chapter 16, Acids and Bases. This is the next to the last chapter. And we'll finish this one and have electrochemistry as the last one. Here we go. Redox reactions is the title, but it's basically electrochemistry. We're not going to do energy. That's off the table. Okay. Let's see what we got here. Just a few sections. This is not a long chapter, but it needs to be by itself because some of the concepts, they take some getting used to. Okay, we're definitely going to talk about acids and bases, but to understand many of the concepts about acids and bases, we need a little introductory. We need to draw from Chapter 17, which is on equilibrium. Chapter 17 isn't part of the overall structure of the course, but there's some concepts in Chapter 17 that will make Chapter 16 more understandable. So let's look at these topics of equilibrium first. When we're talking about liquids, I'm pretty sure we mentioned that when a liquid is in a confined space, and if the liquid has any volatility at all, then some of the liquid will escape into the vapor phase. And if the container is stoppered, if it's sealed off from the outside, then you gradually build up more and more of those molecules from the liquid in the vapor phase. Initially, it's all one way, but eventually you get enough of the vapor molecules in the vapor phase that some of them start returning to the liquid phase. So you get this transfer from liquid to gas, gas to liquid. And as you build up more and more molecules in the vapor phase, the rate at which the liquid evaporates balances with the rate at which it condenses. So you reach a point where evaporation and condensation match each other. Right? And at that point, you can measure a pressure buildup in the vapor phase. Initially, there's not much pressure there because you don't have any added gas molecules from the liquid in that phase. But eventually, you reach a point where it stabilizes, you're at equilibrium, and you can measure a vapor pressure in that space. Okay. On the outside, stand back and look at it. You eventually see the volume of the liquid decrease to a point and stop. And at that point, there appears that there's nothing happening. The equilibrium state appears to be static. But in fact, on the microscopic level, the activity activities that are going on are extremely dynamic. You have very rapid evaporation and condensation going on at the same time. So there are two ways to look at it. And the way to understand it is to look at it from a microscopic level. You've got evaporation and condensation going on at the same time and at very rapid rates, but the rates balance one another. Now, I introduced that part of the concept of equilibrium so that we can talk about chemical equilibrium. The evaporation and condensation is a physical process. We're not changing the identity of the molecules at all. But when we express a reaction in the form of an equation, for instance, just as a generic, we have two reactants and they produce products. Notice I used a double arrow here because chemical equilibrium is analogous to this physical equilibrium in that the rate of the forward reaction will eventually equal the rate of the reverse reaction. So you build up a certain number of products. Well, the products are perfectly capable of reacting and producing reactants again. So you get this forward and reverse reaction. That chemical equilibrium is a very important concept in chemistry and is used extensively to understand how reactions occur and to predict the outcome of reactions. It is also a very dynamic process. This forward and reverse reaction rates are happening at extremely high velocities. But they balance one another. So we're now at an equilibrium state. Now from the outside, of course, the macroscopic observation, eventually it looks like you have some of this left over and you have some of this produced. And they can be expressed as concentrations. Molarity, for instance. Like you have so many moles per liter of C, moles per liter of D, moles per liter of A, moles per liter of B, left over once the reaction stops, and those concentrations appear to be static. They just sit there. Now, once the reaction reaches this equilibrium state, that doesn't mean it can't be changed. Under certain conditions of standard temperature, for instance, temperature, pressure, concentration, starting concentration, whatever those conditions are, then it will reach an equilibrium that can be defined. And we're going to do that in just a minute. But for now, let's say we've reached an equilibrium. We have some of this and some of that. What would happen if you add more of this? Just add more B. That equilibrium system is going to respond. Right? It doesn't just sit there and take it. If you add more of this, that means there are more of these B's available to react with A. So the response then is to produce more C and D, consuming some of this until you reach equilibrium again, until the rate of the forward reaction equals the rate of the reverse reaction. And that's an expression of Le Chatelier's principle. Le Chatelier's was a Frenchman of the 19th century. And that's basically what he said. If the system is at equilibrium and you do anything to disturb it, it will respond in some form to reestablish equilibrium. This is just one way that we've done it, by adding B. You could disturb it by subtracting D, and then it would move to replace some of that D until the rates are balanced again. Okay. All right. That's supposed to be a double arrow. I think the program got confused. Okay, so here's a real world example. So suppose we put these gases, water and carbon monoxide, in a closed container and create the conditions where they react with one another. They will produce hydrogen gas and carbon dioxide gas. And they will keep doing that until the forward reaction and the reverse reaction are balanced in speed. Right? So now what would happen if we add more water? If we add more water, that's a disturbance in the equilibrium, and it's going to shift to the right. Okay? Now, what will that do to the, once we reach equilibrium again, what's the concentration of water? Did it go up or down? Well, initially it went up because we added some, but when it reaches equilibrium, does it go back down to the same place? No, it's higher than it was. It's not as high as it was when we first added the water because we used some of it. But when we reach equilibrium, some of that added water is still there. So we actually did increase the amount of water, water vapor. And in order to reach equilibrium, some of that carbon monoxide that was there had to be consumed. So its concentration will go down. And we will produce more hydrogen and more carbon dioxide. All right. So what if we add more hydrogen? Right? If we add more product, hydrogen, the reaction will go backwards until we've used up enough of the hydrogen and enough of the carbon dioxide to reestablish equilibrium. All right. We can express equilibrium quantitatively with this equation. This is a generic equation. And there again, that box is supposed to be a double barbed arrow. This is an expression, it's called the law of mass action. And I won't go into the history of it right now because what I wanted to do is just introduce the concept so that we can use this knowledge in our discussion of acids and bases. So if you know the concentration, that's what these square brackets mean. The square bracket means what's the concentration of C, D, A, and B at equilibrium. It doesn't matter what you put in there at the beginning. Once it reaches equilibrium, you measure A, B, C, and D, then that square bracket says this is the concentration of these reactants and products. And typically we express that in molarity. Unless we have gases, then we might choose to express it as partial pressure, which is perfectly valid. Partial pressure of each of the components, if they're gases, will be proportional to their concentration in molarity. We know that from Dalton's law of partial pressures. Right? The fraction of each one is related to its concentration. So we can use partial pressures or we can use molarity. Either one will work. But of course, you have to remember, if you use a different unit for A, B, C, and D, then you get a different value for that constant, K. Right? And this, as long as we don't change the temperature, then that K is a constant. If you change the temperature, then the K will change because that is a disturbance and will shift the equilibrium. Right? That's another way to disturb the equilibrium is change the temperature. And then the reaction occurs at a different rate, one direction than it does the other. You get a different equilibrium point and K changes. So if we don't change the temperature, K is constant. Now, the expression is based upon the balanced chemical equation. You have the reactants and their coefficients, A, B, C, and D. Little a, B, C, and D are the coefficients. Those coefficients are part of the mass action equation as exponents. So if we know the equilibrium concentration of C, then we take it to the little c power and do the same thing for all the others. So we write it as the product of products to their individual powers divided by the product of reactants to their powers. And that is the value of K, the equilibrium constant. Okay, so let's take an example. Haber-Bosch, my favorite equation. Nitrogen plus 3 moles of hydrogen yields 2 moles of ammonia, right? If we put this in expression, the product concentration raised to the second power is divided by nitrogen to the first power concentration times hydrogen to the third power concentration, right? There's the coefficient, and that's the power. That will give you a K value, and that K is constant as long as the temperature doesn't change. So whatever we do to change this, if we disturb the equilibrium, then once it settles down and we measure the concentrations again, then in this expression, those new values of concentration will give you the same K every time. Okay, I went the wrong direction, sorry. Now, the K is constant as long as the temperature doesn't change. But remember when we disturbed an equilibrium equation before by adding water. When we add water, then it shifts the equilibrium to the other side in that case, but it left some of that water behind. Right? So now, at equilibrium, we have a different concentration of water. We have a different concentration of carbon monoxide. We have a different concentration of carbon dioxide. And we have a different concentration of hydrogen as products. Those different concentrations represent a different equilibrium position. The equilibrium position is an expression of real concentrations, right? And they can be wildly different as long as at equilibrium, the expression gives you the same constant, okay? So there's a difference between the equilibrium constant and the equilibrium position. All right, here we have, now we're going to look at, all right, we haven't discussed acids and bases yet. So let me give you a little short lesson of acids and bases. An acid always starts with at least one hydrogen. It can have 2, it can have 3 hydrogens, but it always begins with hydrogen, and then it has something else after it, the rest of the molecule, okay? So you got that hydrogen. When you put it in water, it has the tendency to dissociate, right? So it can produce positive hydrogen ions, and it leaves behind a negative ion, right? So in water, that's what happens to it. Now, how far does it go to the right? It depends on the acid. Some go way far to the right, and some go just a little bit to the right. Those are weak acids. But equilibrium is established, and then it can go back the other direction. Right? It can come back this way, go that way. Either way, just like we talked about before, equilibrium can be established for this dissociation process. Now, when we do that, that means we can express this as a concentration. We can express that as a concentration, and we can express this as a concentration. So we can write a law of mass action for this equation. Now, this example, all the coefficients are 1. So if we write the K for this one, we just say that times that divided by that. For our generic acid equilibrium constant. So here's an example of a real acid. This is acetic acid. Right? You know that from nomenclature. Right? We did acids before. So this double barbed arrow says that this undissociated acetic acid molecule can give up a hydrogen in aqueous solution, and then it leaves behind this, and there's supposed to be a sign there, a negative sign on that anion. That's a polyatomic acetate ion. So it should have a negative charge here. Okay, so if we write the equilibrium expression, we want this one times that one divided by this one. So let's see. Looks like this one is the best. Right here. A should be the answer. Okay, that's our equilibrium expression for acid dissociation in aqueous solution. Okay, let's see. This one we're actually going to do a calculation. Okay. So if we have dinitrogen tetroxide in equilibrium with nitrogen dioxide, and we need 2 of them, right, to balance the equation, then we can write the expression for this as, let's see, we're going to have the equilibrium concentration of nitrogen dioxide to the 2nd power divided by the reactant to the 1st power. And now all we have to do, since we're given the values, product value of 060 square it and divide that by 0.055. Then we get a value of 0.065. 0.065 is the K value. Given those data. Now, you may notice that there's a concentration given here and here, but there are no units, dimension units for the Ks. They exist, they're still there. It's just that we never report them. What we do is say, how was this K derived? It was derived from molarity concentrations. So if you look it up in a reference manual, there won't be any units next to the numbers, but there will be a descriptor at the top saying, what were the original concentration units? And it's usually molarity. If it's not molarity, it may say partial pressure. The reason we don't report values for these is because they can become very complex and unwieldy and actually create problems with the calculations. So we leave the units out as long as we know where they came from and we're meticulous about the calculations that we do, then the answers should be correct and in the correct units. All right. So we can make some, we can draw some conclusions about a chemical equation based upon its K value. If the value is very much larger than 1, let's see if I can do it this way, right? If it's a whole lot bigger than 1, then what does that say about the extent of the reaction? What direction does it prefer? Remember, the products are in the numerator and the reactants are in the denominator. So if the value is extremely large, that means we're favoring the numerator, which also means we're favoring products. So we know that for a reaction where the K is very large, much greater than 1, we're looking at a reaction that heavily favors products and only leaves small amounts of reactants behind. And if we look at it the other way, right, if it's, let's see, if the value is very small, much less than 1, then it's the other way around. It favors reactants, and the reaction as written does not proceed extensively toward products. Now, what if we decide we want to write the equation the other way? We want to flip it, right? Put reactants where products are, products where reactants are. That flips the expression also. It inverts the K. So now, if the reaction is written with a very large K value, one direction, then when we flip it, the value of K then becomes very small. Okay. Now, this law of mass action, that expression, that mathematical expression is just like any other equation. If you know all the values in that equation except for one of them, and it doesn't matter which one it is, you can solve for it. So if you already know the K, and you know the equilibrium concentrations of reactants and products with one missing, you can solve for that missing value. Okay, so if the equilibrium lies to the right, this is just a review. Then the K is very large. If the equilibrium lies to the left, then the K should be very small, much less than 1. Notice I don't say anything about what if it's equal to 1. The reason I do that is because it depends on the equation. Because if you have powers of your reactants or products, then that muddies the water. And you may not necessarily find equal numbers, equal concentrations of reactants and products to give you 1. It doesn't always work that way because of the powers. So that's why I say very much larger than 1 or very much smaller than 1, and the in-between is a gray area. Okay, now we can get back to the topic of acids and bases. All right. As modern science approached, beginning in about the 17th century, but gathering steam into the 18th century, investigators, I don't know if we can call them scientists yet, but investigators had a sort of intuition about what constituted an acid. They knew what type of responses it would give in certain reaction environments. They even knew how it would feel, how it would taste, right? You don't want to get acid in your eye or burn, even if it's very dilute. So they sort of had a feel for what was an acid, right? If you're able to taste an acid, it's going to be sour, like vinegar, or like a lemon. That sour taste is due to the acid. Now, you don't want to taste any acid, particularly not in the laboratory setting, because those acids might be hazardous. But many foods taste sour because of the acids. And what was needed was an understanding of why are they sour. Arrhenius came up with the first useful definition for what an acid is. Right. Arrhenius said that acids produce hydrogen ions in solution. And he's talking about here aqueous solution. And bases produce hydroxyls. Okay. So what does that mean? Let's see, I didn't mean to do that. There we go. So what Arrhenius is saying is the molecule must have hydrogen in it in order to produce hydrogen ions in solution. Right? So in an aqueous solution, this is what you get according to Arrhenius. Right? And bases, he said, must have hydroxyls in their makeup. So when they are put in solution, they will also produce hydroxyls. Now, for most acids and bases, well, actually, for all acids, this is true. For most bases, this is true. And they were also interested in how do acids and bases react with one another when you put them together. That's called a neutralization reaction. Well, when they interact with one another, these parts of molecules could care less. They don't react. The reaction occurs between these parts. When you put an acid and a base together, the reaction then is primarily here. The hydrogen ions and the hydroxyl ions get together. And you may notice that HHO, H2O, that's water. When these two get together, you get water. Okay. So why do we need to go any further? Well, as scientists started to use this definition, they found that there are some molecules, compounds, when you put them in water, well, they know that the molecule doesn't have hydroxyls to begin with. It doesn't have hydroxyl in its structure. But when you put it in water, it produces a basic reaction. It makes hydroxyls. So this definition fell apart in those cases. Perfect example. When you put ammonia in water, it produces hydroxyls. Right? Where'd they come from? We need a new definition. So that's where two other scientists come in, Bronsted and Lowry. Independently, they proposed this definition, so they both get credit for it. They approached the concept of acids and bases, excluding hydroxyls altogether. They don't care about hydroxyls. All they care about is the hydrogen ions. So for them, an acid is a hydrogen ion donor. So Arrhenius definition fits that one. This is a hydrogen ion donor. It gives up that hydrogen and it can go someplace. It's donated. Where Bronsted and Lowry differed with Arrhenius was in the concept of the base. The base now is a hydrogen ion acceptor. So whatever accepts that hydrogen ion is a base. That makes this the base. It accepts that hydrogen ion. That's one example. But back to our example of ammonia. Ammonia then can accept the hydrogen. If we say that it's a base, where does it get its hydrogen? Right? We just put it in water. That's all there is there. Ammonia and water. So the only place it can get hydrogen, well, two possibilities. It could get hydrogen from another ammonia, or it could get hydrogen from water. So if we react it with water, and we take one of these hydrogens here and donate it to that ammonia, that makes this an acid. It's a donor, and this is an acceptor. Now what we get is the ammonium polyatomic ion in solution and a hydroxyl in solution, right? Because when you take hydrogen away from water, that leaves behind your hydroxyl. Okay? So that explained how you could get a basic solution out of a molecule that has no hydroxyls to start with. And that serves for almost all. In fact, it does serve for all aqueous environments. Bronsted and Lowry solved that problem for aqueous environments. There are some interesting reactions, particularly organic reactions, where this won't work anymore because you don't have water. Right? And then we need another definition. And I'm not sure if I've got that one here. No, I think I left that one off, at least for now. We may come back to it. Don't worry about it now. If I don't mention it, just, you don't even have to think about it. Okay, here's our example where this is our acid, right? Hydrochloric acid reacts with water. It transfers a proton to water. Now this is the acid, and water becomes the base. It's a proton acceptor. So when it accepts the proton, it makes this funny ion, H3O plus, right? A water molecule with an extra hydrogen on it. That's known as the hydronium ion. And it leaves behind the chloride ion, right? We've transferred from this acid to this base. Okay. So this is typically what happens to an acid when we put it in water. And up to now, I've been writing the acid dissociation as this type of equation. That's for convenience and for clarity. We show that the dissociation of this acid gives a proton and what's left over. But in reality, what happens is the proton is transferred from here to a water molecule like this. And in fact, in the real world, hydrogen ions never exist by themselves. They're never alone. They're always attached to something or in the process of being transferred from one place to another. You never find hydrogen ions out by themselves. Now, that being said, we don't always write them that way because it's more convenient to write them this way. Okay, so I just wanted to make that point. It's okay to write them this way, unless you need to express them this way for some purpose. Okay. So more definitions. According to Bronsted and Lowry, the acid donates a proton and the base accepts a proton. And then when you produce products as a result of that reaction, you get the base that accepted the proton now has that extra proton. And it can act as an acid. It can donate that acid, that proton, to a base. So we call the result of this base accepting a proton. Now it produces a conjugate acid. So bases produce conjugate acids, and acids produce conjugate bases. Right? This one lost a proton. Now it produced a conjugate base. Under the right circumstances, that base can now accept a proton, and it can go back to where it was right here. And in terms of equilibrium, that's what happens. Once you put this in water, then it will go this direction, and then it'll also go backwards, right? Until the rates are balanced and you have equilibrium. Okay. Now, notice one other thing. When we write these equations for the loss of a proton from an acid, it's always one proton at a time. We don't lose two protons at a time. The equilibrium process says that only one proton transfers at a time. If you have more than one proton, for instance, if we have sulfuric acid, right, and we're reacting it with water, then it'll transfer a proton to this water, and what's left behind? The hydrogen sulfate polyatomic ion is left behind. That is a valid equation. Now, sometimes we express the overall equation. If we take this one now, then it also can transfer a proton to water, make the hydronium, and now you have sulfate left behind. Okay? So this one has a K value, and we use a subscript of A, meaning acid dissociation constant. So this is an equilibrium constant for an acid. And since this one has two protons, we say that one's the first one. And this one will have one, and we say that one's the second one. And each reaction has its own equilibrium constant. And they will be different, sometimes very different. All right. So this is an attempt to show you what happens to that hydrogen because, like I said, hydrogens don't just float out on their own. You can make them do that. I'm not saying they can't be made to do that, but in this environment, they're never alone. You could take a molecule and put it in a gaseous phase and bombard it with electrons or some, make a plasma out of it. Then you would have individual hydrogen ions floating around. But that's not this environment. That's completely different, and we're not going there. So we transferred a hydrogen to this water molecule and made a hydronium and left behind the chloride ion. All right. So which of the following represents conjugate acid-base pairs? How do you determine conjugate acid-base pairs? Well, you got to have an acid, and then you have to lose one proton. from that acid to make its conjugate base. That's what we mean by a conjugate acid-base pair. Let's see. Wrong direction. There we go. Okay, so notice that two conditions have to be met. First of all, the acid has to lose one proton only. Okay? And second of all, you cannot change the nature of that part of the molecule, right? If you've got this here, you got to have it there also, right? So the A selection right here hasn't lost a proton, and the anion part of the molecules are different. So that can't be right. How about this one? What happens if you lose a proton from the hydronium ion? What do you get? You get water. You don't get a hydroxyl. How about this one? Sulfuric acid to sulfate. What's wrong with this one? Well, you've got sulfate on both sides. That's okay. But you've lost two protons. And that's forbidden. You can't do that and make an acid-base pair, a conjugate acid-base pair. So here you have hydrocyanic acid. Remember our nomenclature? Lost a proton, makes the cyanide ion. That's the ticket. Right. There's your conjugate acid-base pair. And here's a description of just what I told you. All right. So now, I used a term earlier, weak acid. We need to define these terms. Let's start with strong acids. Chemically speaking, you may have an intuition about what strong or weak acid may mean. And most often, those who have not been trained in the sciences or in chemistry tend to think of strong versus weak acids in terms of the effect they have on your physiology. In other words, a strong acid is anything that will burn your hand, and a weak acid is one that won't burn your hand, for instance. But in chemical terms, a strong acid has nothing to do with this physiology. It has to do with the extent of dissociation. How far is your equilibrium? Is it way to the right, producing products, hydrogen ions and conjugate base? That would be a strong acid. It's basically completely ionized, complete dissociation. Right? So this would give you way to the right and no return, or imperceptible return reaction. That's a strong acid. A weak acid, in chemical terms, is one that does have an equilibrium situation where you have acid, water, produces hydronium ion, conjugate base, but the hydronium and the conjugate base can react in return to the reactant side. And also, the undissociated acid in an aqueous solution on the reactant side is mostly where it's located, with very little on the product side. That's a weak acid. Most of the acid molecules remain intact. Example, the acetic acid molecule. When you put it in solution, most of it stays as the acetic acid molecule, undissociated. In fact, if we write that equation out, like this, and I'm going to use the abbreviated form, okay? So I've left out the water molecule for this expression. Then you get that plus this. And if we write the K value for that, then we would have this, 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 and that value at standard temperature, 25 degrees Celsius, is, let's see if I can scratch my head. I think it's 1.5 times 10 to the minus 7. So 10 to the minus 7 means that there's very little of this and a whole lot of that. That means, since it's much less than 1, that it's mostly over here. And just a little bit that direction. That's what a weak acid means. There's very little acid dissociation involved. And this is the artist's idea of what that means. Strong acid means that you got nothing of this left and you've got hydrogen ions, or hydronium ions in reality, and the conjugate base. Whereas with the weak acid, it's mostly over here. Well, when the reaction occurs, you got most of this left over and just a little bit of that in solution. Okay, so the other concept, I'm going to leave that up there for now. The other concept is that to recognize that if you have a strong acid, it produces the conjugate base. Say hydrochloric acid produces a conjugate base, Cl minus, the chloride ion. Well, if the acid is strong, that means it wants to give up that hydrogen completely. And once it reaches the conjugate base side, does it want to come back? No, it got rid of all its hydrogen. It don't want them back. Right? So that makes the conjugate base weak. It does not want hydrogen. So bases are judged on their strength that's based upon how strongly do they want to attract or accept a hydrogen ion. Right? So if you have a strong acid, you get a weak conjugate base. So you probably already figured out, if you have a weak acid, then the conjugate base is strong because it wants to be back on that other side over here. All right? There's very little of this because it wants to be over here. So if you put any more of this in there, it's going to snap it up and go back this way. So that's what this chart is trying to explain. If the strength of the acid gets weaker and weaker and weaker, then the conjugate base gets stronger and stronger and stronger. And we can quantify that. Right? We're not going to do it in this class, but it can be done. Okay. Let's see. Ionization or dissociation of an acid. Right? For strong acids, the forward reaction predominates. For weak acids, the reverse reaction predominates. The strength of the conjugate base, and we're comparing this to water also, is for strong acids, the conjugate base is very weak. Right? It will not accept hydrogens from either hydronium or from other water molecules, for that matter, because there are lots of them there. But it doesn't want them. Weak acids, on the other hand, produce a strong conjugate base. Okay, what are some common strong acids? Sulfuric acid is a strong acid. Now that begs the question, which hydrogen are we talking about? Right? For sulfuric acid, it's a strong acid because that first hydrogen wants to go. Right? It's completely dissociated. So you end up with hydrogen sulfate ion as the conjugate base. is a weak base, whereas H2SO4 is the strong acid, right? Now, the HSO4 minus ion has a different character than the H2SO4, right? Once you pull a hydrogen off of that H2SO4, okay, goes all the way over here. Right? Now, just think about it. How hard is it going to be to remove that proton from this molecule? This is a negative ion. You know how hard it is to remove a positive from a negative when they're that close together? It's very difficult. So this is a strong acid. This is a weak conjugate base. But now if we take this one and we try to dissociate that, this is a weak acid. It's very difficult to remove that hydrogen from this anion. So that makes this one a strong conjugate base. That concept is universal for polyprotic acids. If you have two or more hydrogens that can be dissociated, that's their behavior. Now, the first one may not be strong. Right? The first one could also be weak, but this one will be weaker. Always. Okay. Other strong acids, hydrochloric acid. Right? It's only got one proton, so that's a non-issue. It just loses that proton and it's happy as chloride ions and hydroniums. Nitric acid, it only has one dissociable proton, so it also is strong and makes the nitrate ion, which is a very weak base. Perchloric acid, that is exceptionally strong acid. Produces the hydronium ions in solution and the perchlorate ion. All right. So you remember your nomenclature, right? If there's oxygen in the molecule, you don't say hydro. That's the point I'm trying to make here. It's not hydronitric acid. It's hydrochloric acid because there's no oxygen, right? Think back to our nomenclature. This is simply nitric acid. Just a reminder. Okay. So acids that have oxygen in the conjugate base side can vary in strength. And their strength varies is proportional to the number of oxygens in the molecule. These oxyacids, they run in families. Right, so we can have, for instance, H2SO4. We can also have H2SO3. Right? Sulfuric acid, sulfurous acid. Which one's stronger? This one is stronger because it has more oxygens. Now, I'm not going to try to explain why that is. It just is. More oxygens makes the stronger acid. This is actually a weak acid. And you can do the same thing with other oxyacids. Okay, these oxyacids are known as mineral acids, right? Because they have no organic backbone. Acetic acid is an organic acid. And organic acids typically have not always, but typically, have this part of the molecule, right? A carbon, that's called a carbonyl, or double bonded oxygen, a single bonded oxygen with a hydrogen. That hydrogen right there is the one that dissociates. For that reason, we often write acetic acid, right? C2H3O2. We often write that as this carbon with its hydrogens, right? Those three hydrogens on this carbon. Then there's another carbon, the second one. And then on this carbon, we have there, one of those oxygens, the other oxygen, and that hydrogen. This is the hydrogen that dissociates. And that's common for a great many organic acids. This is the organic part of the molecule. This is the acid part of the molecule. And they're all weak acids. For safety reasons, if you ever are confronted with the necessity to store types of concentrated acid and organic acids, you always keep the organic acids separate from the mineral acids, just as a rule of thumb. There's some mineral acids that are compatible with the organic acids, but if you can't remember that, just keep the mineral acids and the organic acids separate and you'll be safe. If you get the oxy acids, the strong oxy acids like nitric or sulfuric or perchloric, in a spill combined with an organic acid, you will have an explosion. I can't go into the details right now, there's not enough time. But just as a safety matter, keep them apart. Okay, lactic acid is an organic acid, and you'll see there's the acid part right there. Lactic acid is that stuff you build up in your muscles when you exercise and makes you sore. Formic acid, right? The very simplest organic acid. It has this part of the molecule, but it only has a hydrogen on the end. So over here, there's a hydrogen. Formic acid. Anybody who's ever been bitten by a fire ant knows formic acid. Right? The cocktail, when a fire ant bites you and spits into the wound, the cocktail contains formic acid. It has a bunch of other stuff too, but formic acid is enough. And it burns. It burns like crazy. And the bad thing about fire ants is they never come alone. They always bring their cousins, and lots of them. So if you accidentally kick a fire ant mound and you're not paying attention, they will be up your leg, and one of them has a little bugle, right? When your legs get covered, then one of them blows the horn and they all bite at once. And that's when you're seen running across the field, coming out of your pants. Uric acid. Okay? Uric acid is a nitrogenous waste product. For some animals, it's their principal way of expelling extra nitrogen from their bodies. Humans, all mammals, expel nitrogen waste as urea. Right? That's why they call it urine when you go to the restroom. It's composed, it has urea and other things, but the urea gets rid of the nitrogen. And for birds and some reptiles, they use this molecule to get rid of excess nitrogen, predominantly from protein metabolism. But it's an acid, right? One of these hydrogens, I slid off to the side there. That's a carbonyl oxygen, there's carbonyl, there's carbonyl. There's your nitrogen. One of those, probably this one right here, is the acid hydrogen. Why do I say that? Because it's got two oxygens on either side. Whereas this one only has one oxygen and that one only has one oxygen there and there. So the one with two oxygens is probably more acidic. It's more likely to leave. So this is the acid hydrogen right there. But it's called uric acid because it is an acid. It's a weak acid, but it's an acid. Citric acid, right? Lemons, grapefruit, even oranges have this stuff in it right here. Now, the way we write these molecules, I didn't explain that. We write organic structures. It's typical wherever you have two lines coming together, right? There is an atom there. But in organic chemistry, we don't write the carbons. It gets too busy. So that's a carbon, that's a carbon, that's a carbon, that's a carbon. This is a carbon, 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 carbon. Okay? Now, if we have any other atoms in there, we usually write them in. Except sometimes we leave the hydrogens out too. Right? So this one's going to have a carbon there, and it's bound to a carbon here, and it's bound to a carbon here. But it also has two hydrogens. But they're not acidic hydrogens, so we're not concerned with them right now. The acidic hydrogens, this one, and that one. So citric acid has three acidic hydrogens. And each one has a K value. Right? If you lose one hydrogen, then the next hydrogen comes off with more difficulty. And the third one comes off with even more difficulty. For the same reason as before, because you're making an anion and it's hard to remove a positive ion from a negative. Okay, so that's citric acid. And it's an organic acid. All right. So we are going to have some calculations. Not many, but a few. If you have a 1 molar solution of hydrochloric acid, then put these things here in order of strongest to weakest base. Okay? So we've got hydrochloric acid that's dissociating completely. Right? So this is a strong acid. This is a very weak base. Okay. We also have this hypothetical acid. It's a weak acid that produces this plus this. Okay. So now those are our choices along with water. And water can accept a proton. But it doesn't accept a proton as well as this weak acid. This weak acid is actually this acid is stronger than water as an acid. So that makes the base weaker than water as an acid. Excuse me. This is weak, strong. As a base, this is weak. Okay, if we're going to put them in order, we have to decide which one is the weakest. Right, strongest to weakest. So the weakest is going to be chloride. That's the weakest base. The strongest base is going to be this one. And in between is that. So that's in terms of proton acceptance. This is the strongest acceptor of protons. This is the weakest, and water is in the middle. Right? Chloride is very weak as a base. A- is a good base. because HA is a very weak acid. And water's caught in it. Okay, that's the logic behind solving this problem. How about acetic acid and hydrocyanic acid? We're going to do a comparison here. So acetic acid, let me see how far along that is. Okay, I'm good on time. Acetic acid, here we go. Only one hydrogen. C2H3O2, right, produces this in abbreviated form, and this, the acetate ion. And hydrocyanic acid produces this plus this. Okay? Now, they're both weak acids, but acetic acid is stronger than HCl. So this is stronger, this is weaker. But they're both weak. So that means this one is going to be a weaker base, and this is the stronger base. Right? It's just the opposite. Now, what's the question? Arrange the bases from the weakest to strongest. Okay? So we know how to compare these two. This one's a weaker base than that one. So we're going from weakest to strongest. This is the weakest, weakest, weakest. 4 of them. 1, 2, 3, 4. What is the absolute weakest base in this bunch? It's the one from the strong acid. That one right there. So this is the weakest base in that list. How about the strongest base? The strongest base comes from the very weakest acid. Now what we have to do is say, where does this one compare to water? This one is a little bit stronger than water, I would say. So that puts water here. Let's see. Okay. We're going to have a discussion of water dissociation itself. Hold on a second. Just a second here. I lost the flow. How did that happen? Weakest to strongest. They're saying that water is a weaker base than chloride. I think that's wrong. Weakest to strongest. That order is wrong. This is the strongest base because it's stronger than this one. This is the weakest base in water is here. So that order is wrong. I need to fix that. Okay. So now, if you have a container of pure water, there's nothing else in there. It's a pure substance, water only in that container. What's it going to do? Well, we've discovered that on a very limited scale, those water molecules will react with one another as acids and bases. So, oh, we got it on the board already. You can get one water molecule will act like an acid and the other one will act like a base. So the acid will donate a proton to the other water molecule, and what you get is a conjugate acid of the base and a conjugate base of the acid. Okay? Now, one rule that I didn't mention before. We can write we sort of skipped over some things here, going from here to the K value for that reaction. What we're saying is that when you write an equilibrium expression, if you have something dissolved in the liquid, it has a concentration. You keep that. If it's a gas, it has a variable concentration. You keep that. If it's a pure liquid or solid, throw them out because their concentrations do not change, effectively do not change. So in this case, that's a liquid and that's a liquid. So it would normally be part of the denominator, right? We would put it down here. Except that we throw the liquids out. Pure liquids are gone. So all we have left is the hydronium concentration times the hydroxyl. And for convenience, we write the hydronium as hydrogen ions. So that's why this expression looks the way it does. The K value for the dissociation of water at 25 degrees Celsius is always 1 times 10 to the minus 14. Okay? So if we know the concentration of this one, we can calculate the concentration of that, and vice versa. And anytime you put an acid or a base into aqueous solution, you get that acid or base doing its reaction, but at the same time, you always have this one going on along with it. Of course, if the equilibrium constant is larger for the acid that you put in solution, then this one may not be significant because it's such a small value. Okay. It gets this special subscript, KW, and water dissociation is the only reaction that gets the KW. So when you see KW, it always means this. Let's see. I don't know where this one came from. Why are we saying this? X is the expression for equilibrium concentration of X. That's just a reminder. Right? Anytime you have square brackets, that means equilibrium concentration. If it's not equilibrium, then we may use parentheses. But we're not going to go there in this class, just not enough time. So we'll always use square brackets. Oh, okay. I don't have to correct that one because the answer to the previous slide is located right here. Oops. Here we go. Okay. This nature of water to react with itself, actually with its neighbor, water is called amphoteric. Ampho meaning both. Why do we say both? Because this water can act as an acid or a base. Which one's the acid and which one's the base? Who knows? It can go either way. This one could be the acid. That would make this one the base. But just as easily, we could call this one a base. And this one the acid. It would still produce a conjugate acid and a conjugate base. Okay, and remember, the Kw for this expression is 1 times 10 to the minus 14. That is a very, very small number. What that means is it's over here, right? Most of it is over here. You produce just a tiny amount of this, which means this is a very, very, very weak acid, which makes this a very strong conjugate base. Or this is a very weak base. That makes this a very strong, a very weak base. That makes this a strong conjugate acid, right? So you get weak, weak, strong, strong. As long as it's just water and water doing its amphoteric thing. Okay. I'm just making a point here. No matter what you put in solution, this reaction is always happening. Always, always, always in aqueous solution. Okay. So I'm going to leave that up there. Let's go back to this one. Acid. Okay. 3 possibilities. Right? In solution, if it's just water, nothing else, then this is equal to that times. Right? That's the expression. So what does that mean? Since they came from the same source, these have to be equal. 10 to the minus 7th molar and 10 to the minus 7th molar. That's the only way you can get this expression from pure water. This one has to be equal to that. And multiply them together, you get 10 to the minus 14. This is a neutral solution. It's not acid, it's not base. It's neutral. When these two are equal to each other. Now, this is for pure water at 25 degrees. But by extension, if these concentrations are equal to each other under any other circumstances, it is neutral. Now, if the temperature is 25 degrees, right, this is always going to be the case. 10 to the minus 7, 10 to the minus 7. It won't change. If you change the temperature, then this equilibrium changes. But you still have a neutral solution if these are equal. But we're going to stick with 25 degrees so that all you have to remember is 10 to the minus 7, 10 to the minus 7. That's neutral. If we put something in the solution that favors the acid, this one, makes this one bigger, what happens to that one? Well, remember, this reaction is always going on. So that means if this one is, say, 10 to the minus 6, because we added some acid to it, what does this one have to be? It has to be 10 to the minus 8 to make that 10 to the minus 14. That's an acidic solution. Go the other direction. So we put a base in there and make this one 10 to the minus 6. That one has to be 10 to the minus 8. That's why I made the point that this reaction is always, always, always active. So when we change these concentrations, then we have to balance this one as well as the other one. Say it's a weak acid, whatever these tend to be, then we can calculate the other. Okay. In an acid solution, which one of these is correct? Well, let's see. Hydrogen ion is less than that? No. That's basic. Hydrogen ions greater than that? Yep. B is true. Hydroxyl ions greater than that. That would be basic. Hydroxyl is greater than hydrogens. That was also basic. So the only acid here, and the only correct expression, is that one. That is an acid aqueous solution. The others are basic. All right. So if we have a solution in which the hydroxyl ion concentration is measured at 2 times 10 to the minus 10 molar, what's the hydrogen ion concentration? Right? If we have this times this equals this, right? I left out the 1 because that's the same thing. Then if we put in 2 times 10 to the minus 10 here equals this, then how do we solve for that? It's just 10 to the minus 14 divided by 2 times 10 to the minus 10. Okay? So can I do that? I can't do it in my head, but I can do it on the board. Okay. Well, if this is 1 times that, then this is also 1 divided by 2 times 10 to the minus 14 divided by 10 to the minus 10. So what's this one? This one is 10 to the minus 4. And this one is 1/2. So that would be 5 times 10 to the minus 5 molar. And by the way, is this acidic or basic? Well, that's bigger than 10 to the minus 7, isn't it? So it's acidic. Okay. So the answer is that one. I use a trick here. Actually, it's not a trick, it's a mathematical expression, right? I separated these two. That fraction times this. Right, that's perfectly valid. Let's see, I left out that part. There we go. Otherwise, use your calculator. Okay. Now, we've got this hydrogen ion concentration that for many calculations is going to be a very small number. 10 to the minus 5, 6, 20, whatever. And those numbers can very rapidly become unwieldy. So, question? Okay, I thought I heard a question. There was a chemist. Actually, he was a chemist, but he was also working with living systems, who was interested in developing an expression for acidity, hydrogen ion concentration, that was easier to handle, right? He was familiar with logarithms, and he knew that he could reduce these unwieldy numbers to a more compact form if he just took the log of the number. His name was Sorensen. Okay? So what he did was, and that's more information than we need right now. What he did was he took the hydrogen ion concentration, right? Whatever it happens to be, 5 times 10 to the minus 5, for instance. And he took the log of it. But if you have a number here with, say, 10 to the minus 5, what is the log of that number? Right? I left off the coefficient just for convenience. Right? If we take the log of that number, right, based on common logs, then the log of this number is the power of 10 that's equal to that number. And what's the power of 10 that's equal to that number? It's equal to minus 5. Correct? Minus 5. He didn't like minuses either. So he got rid of the sign. He said, just make a minus out of it. Now we got a plus number. Okay, so that was Sorensen's solution, and this is called pH. Little p, big H. How do we deal with significant figures, though? The rule is the number of decimal places in the log is equal to the number of significant figures in the original number. So if the original number is 1.00 times 10 to the minus 5, and we take the negative log of that, we get a positive 5, but we also have 1, 2, 3 significant figures, means 1, 2, 3 decimal places. Okay? Now, what if you're given that number? This is pH. But you want to know, what is this? Well, all you have to do is go backwards. Right? Put the negative over here. Negative 5. And then resolve this. So we need the anti-log of that number. Anti-log of minus 5 is equal to this. Well, how do you do the anti-log? We don't use tables anymore. I mean, when I got started, you had to use tables. We didn't have calculators. But on your calculator, you have a key that says LOG. That's log. That's the one you use for this direction. And then there's a function. You press the function key, and above, usually, above that log key is a little symbol that says 10 to the x. 10 to the x is the anti-log of log. So this would be 10 to the minus 5 power. Okay? And then you would just resolve that in your calculator. 10 to the minus 5 power is the hydrogen ion concentration. And then you would say 3 decimal places. You could keep 3 significant figures in your coefficient. Okay. Let's talk about pH range. On a scale, okay, and we're going to say we get more acid as we go this direction. And we get more basic as we go this direction. So where's neutral? Neutral's right here. Right? And at neutral, we know that the hydrogen ion concentration is equal to the hydroxyl ion concentration is equal to 10 to the minus 7. Right? Both of them. What's the pH of 10 to the minus 7? It's the power of 10 that equals that value. 10, and then take the negative of it. So 10 to the minus 7, the log of 10 to the minus 7 is minus 7 times minus is 7. So neutral is a pH 7. Okay? So what happens when we go this direction? Well, this direction we get increased concentration of hydrogen ions. So we would have maybe 10 to the minus 6 would be greater than 10 to the minus 7, 10 to the minus 5, 10 to the minus 4, right? On up. Well, what's the pH for this one? And this one? And this one? So as you become more acidic, the pH value gets smaller. And that's simply an artifact of the logarithmic transformation. Plus, we made a negative out of it, right? The negative log. So we go 7, 6, 5, 4. So you should know that going the other direction, 8, 9, 10 is more basic. So numbers bigger than pH numbers bigger than 7 is a basic solution. There you go. And there's a typical range of things, right? Stomach acid is in the neighborhood of 2, unless you eat lots of tomatoes. Or you're Italian, you like tomato sauce. Then the pH of your stomach acid is going to drop down maybe around 1. Vinegar is a little higher in pH. Milk, pure water, of course, is 7. Milk is a little acidic. Blood is a little basic, right? Anybody that's had anatomy and physiology knows that the normal range of pH for your blood is 7.35 to 7.45, I believe, if memory serves me. Household ammonia is going to be very high pH. And then sodium hydroxide is even higher than that. 1 molar sodium hydroxide. Okay. So the moral of this story is, let's see. Answer the question, can you have a negative pH value? Can it go to, say, -1? Well, think about it. If that's pH equals -1, what does that mean? Well, take the negative of it, and the hydrogen ion concentration would then be 10 to the first power. Okay? So that would be equal to 10 molar. So if you have a concentration of acid, particularly strong acid, that's 10 molar, the pH can be -1. Now, that doesn't have much of a practical application for 2 reasons. One is, if you've got that high concentration, then you might as well use molarity. But Sorensen, who invented this thing, was looking at living systems. And he rarely encountered pHs outside the range between, say, 2.5 to 11 or 12, always in that range. But mathematically speaking, you can have a negative pH, right? Simply because of the nature of the transformation. All right. So, I got 20 minutes. I think we can make it. Calculate the pH of each of the following. Okay. So we have a solution that's 1 times 10 to the -4 hydrogen ions. So negative log of what? 1 times 10 to the -4. That's an easy one, because this is the same as 10 to the -4. So the negative log of that would be 10 would be negative. Excuse me. Well, it'd be 4. Okay. Let's see. We've got 2 significant figures, 2 decimal places. How about this one? What's the pH of OH minus equal to 0.040 molar? Well, we need hydrogen ions, don't we? So we would find out what's the hydrogen ion for this one? remember that this expression is always working. 10 to the minus 14 equals hydrogen ions 0.040. So solve for hydrogen ions equals this one divided by that one. This is 4 times 10 to the minus 2. And this is 1 times 10 to the minus 2. So this is 0.25, right here. And this is minus 14, minus 2 in the denominator means minus 12. Right? So it's 2.5 times 10 to the minus 13. Now we need to take the negative log of that. So I need my calculator for that. All right, 2.5 with an exponent of minus 13. Okay. And then take the log and change the sign. So I get 12.6 pH. All right. That was easy. This one takes a little doing. There you go. Oh, two significant figures. So I need a 0 here, don't I? There we go. And that 4 actually needs 2 decimals. So that one's wrong. Technically speaking. All right. So we got another problem here. If your solution is 5.85 pH, what's the hydrogen ion concentration? Well, use our definition, 10 to the minus 5.85. So all I have to do is say 5.85, change the sign, and let's see. 2 decimals means 1.4 times 10 to the minus 6 molar. Think now when that one's wrong. Right? That's 3 significant figures. And the pH only had 2 decimal points. I need to work on that, don't I? Okay. Now, pH is a mathematical transformation, a logarithmic transformation. So we could use that same procedure for hydroxyl ion concentration too. Right? It's mathematical. And we can call the negative log of the hydroxyl ion concentration is POH. Okay. So if we say, if we calculate the pH and POH, what if we look at our equilibrium expression, KW? Actually, we can go even further. We can take the negative log of the K value, PKW. So what would that be? Well, if we start with this expression, right, KW equals hydrogen ion, hydroxyl ion concentration, and then take the negative log of the entire expression, then the negative log of KW is over here, and the negative log of this expression is here. But in logarithmic terms, if you take the log of a product, the log of A times B is the same as the log of A plus the log of B. Right? That's from math class. And that's what we're going to do next. Right? This becomes negative log of that one plus the negative log of this one. So now that we've got everything separated, and these are negative log, negative log, negative log, we can insert our P expression. So before we do that, we're going to put the actual value in here for KW. So the negative log of that value is 14. Right? It's PKW, but it's also 14 at 25 degrees. And then this is pH, and that's POH. So pH plus POH is PKW. All right, so what if, let's see, I think we're going to have a problem to solve here. Yeah, here we go. Calculate the POH for each of the following. So for this one, I would just calculate, this is B, negative log of 0.040. So what is that? 0.040 log, change the sign. It's, let's see, two significant figures. So I'd say 1.40. How about this one? What's the negative log? Well, POH, right? How would we get POH? Well, we could go back to the original expression, find out what OH is, and then take the negative log up. But why don't we make it easy on ourselves? What's the negative log of 1 times 10 to the minus 4? That's pH. Okay. So this is going to be two decimal places is pH. This is POH. But we want POH from this one. Well, we know that 14 is equal to pH plus POH. That means POH is equal to 14 minus 4. That's 10. Okay? That makes it a little easier, doesn't it? And this one's just a straight calculation, 1.40. So there's the answer to B, and there's the answer to A. All right, I got 10 minutes. Let's see. We're close to the end. Check myself. Pretty close. I want to talk about buffers in a second. Let me see if we need to deal with this one. The pH of a solution is 5.85. What's the OH? All right, for this one, I would calculate, use our relationship of PKW equals POH plus pH. And there's POH, 8.15. Oh, it wants to know the concentration. Then you would take the anti-log of the negative POH. And that gives you the POH concentration in molarity. Okay. How do we calculate the pH of a strong acid solution? Remember, strong acids completely dissociated. So if you put 2 molar hydrochloric acid in solution, what's the hydrogen ion concentration going to be? Well, for every 1 HCl, you get 1 hydrogen ion. So the concentration is going to be 2 molar hydrogen ions. And then all you have to do is take the negative log of that value, and you get a negative 0.3. There's your negative again. It's simply an artifact of the transformation, the expression of pH. Okay. All right, so here it is. I mentioned earlier, between 2.5 and 10.5 is the typical range. And in fact, we have electronic devices that will measure pH directly. And well, they're called pH meters. And they have a probe. And if you're going to measure the pH of a solution that's less than 2.5 or greater than 10.5, then you need a special probe that's designed for that environment. Otherwise, it will give you an inaccurate reading. May even destroy your pH probe. Okay, how about this one? Aqueous solution of HCl is 2 times 10 to the minus 3. What's the pH? Well, there's a hydrogen ion concentration. We just take the negative log of it, and the pH is 2.7. How about the pH of 1.5 times 10 to the minus 11th molar HCl? Well, in this case, what's the concentration of hydrogen ions in pure water? Well, the concentration of hydrogen ions in pure water is actually greater than that. So if you think you're making an acidic solution by adding this much hydrochloric acid, you're wrong. It's not high enough to affect the equilibrium of the amphoteric water. So the pH is going to be 7. Right? It's still going to be 7. You have not put enough hydrogen ion in there to influence the pH at all. All right. What's the pH of this one? Okay. Nitric acid at this concentration. Okay, that is significant. That's much, much greater than 10 to the minus 7. So we do a straight calculation. And that pH is 1.82. Actually, it should be 1.820. Why? Because that's three significant figures. We need 3 decimal points. Okay, last topic, buffers. What is a buffer? A buffer in terms of acidity is a solution that resists a change in pH when you add acid or base to it. Okay? So there must be some kind of reaction going on in that solution. If it's not going to change pH very much, it will change a little bit, but a buffer won't change much. When you add acid or base to it, well, there's got to be a reaction in there that's consuming part of what you add. It's got to be a Le Chatelier situation, right? You've got a solution at a given pH, it's at equilibrium. Then you add something to it, hydrogen or hydroxyls, and that disturbs the equilibrium. So it's going to move, right? But how far it moves depends on nature of what's in the solution. And that's where we come to the character of the buffer. It's nearly always a weak acid and a conjugate base of the weak acid. That makes a buffered solution. So if we've got this acid, which is weak, in equilibrium with its conjugate base and hydronium ions, or hydrogen ions in this abbreviated form, where does it want to be? It wants to be over here, which means that's a very strong base. So if we add hydrogen ions to this solution, it's going to go like that. It's going to consume most of those hydrogen ions with this strong base, right? What does that do to the pH? Well, the pH was here, right? If we add these, but most of them are consumed, it's almost exactly where it was to begin with. Okay. That's why we need a weak acid making a strong conjugate base. It consumes hydrogen ions. That takes care of hydrogen ions if we add hydrogen ions. Okay. Let's see. Right. Any added hydrogen ions react with the strong conjugate base. Okay. Just like that. How about the hydroxyls? If we add the hydroxyls, right? What are the hydroxyls going to react with? The hydroxyl is the strong conjugate base of water. So if we add hydroxyls, what are they going to do? They're going to go for hydrogen ions. Right? This expression here says that it's going to react with this weak acid. Okay, I'll buy that. It could react with this one. What is it going to produce? Well, it's going to produce water and more of these, right? Has it changed the hydrogen ion concentration? Not a bit. What if instead it reacts with this? Makes water. What's going to happen? If you remove some of these, this is going to shift that direction and replace them, right? So either way, you've stabilized the concentration of hydrogen ions. Consequently, your pH doesn't change much. It always changes a little bit, but not like it would if you had a strong acid in there and you tried to do that. If you have a strong acid and you add acid or base, then the pH goes wildly in either direction. It has to be a weak acid in order to produce a buffered solution. Okay. Oh. I said most of the time we make buffers with weak acids and their conjugate bases, but you can also make a buffer with a weak base, like ammonium. So that's what this problem is doing. Okay, we're going to take a solution of ammonia to which we have added ammonium chloride. So just about out of time. So if we have ammonia here, and we're going to add ammonium chloride, that makes ammonia there. Okay? So this reaction then goes that way and that way. Right, so we've added some of this together. Now we have our equilibrium situation set up. So what reaction will occur if you add strong base, such as sodium hydroxide? Well, if you add hydroxide to it, that adds this, which means it reacts with that and goes this direction. So you're going to have this plus this, and you get this plus this. Okay. Well, actually, I should have said this. Sodium hydroxide plus ammonium ion. This is a spectator plus this plus that. So that gives you the answer that they're expecting. Okay, that's it. So have a look at those. Have a look at these problems that you'll find in Brightspace. And next Tuesday, we'll look at those in earnest and solve some problems on the way to taking an exam next Thursday. Questions or problems before we go? 5 seconds, according to my watch. We'll see you next week.